evening, ladies and gentlemen. I want to take the opportunity to show you some of the results which we obtained when we last year finished a research project which was financed by these people here, Research Association of Automobile Techniques or something like that in Germany, and now you see the background. It's an idea which was not born in my brain, but these automobile manufacturers wanted to know that. And I use now a title chart, three-dimensional notches, to hide a bit what's going on. Really, I'm going to talk about weld ends. So weld ends, here you see a weld starting point and a weld end point, and you see obviously this is a tube, or actually two tubes put into another and then welded with a lot of ends. And in order to explain all the stuff, I have brought one of these specimens with me, and you can see what I tested here. And these are these two tubes. They are now on their round through the audience, and these tubes have been loaded under nominal, under normal force and torsion moment. And this is a cross-section view. That is the inner tube and the outer tube. And in these quarter circles, there is a weld, a seam weld with a starting position and an end position. The dimensions you see on the screen and also on the specimen. This is just a movie of the production process. It is done by Benteler, and it is done as they weld together chassis and suspension components and such things. You see here the specimen, the inner tube, the outer tube mounted in this rig. And now two robots come here and place here these two welds on a quarter circle, and that's it. And then this specimen went into the machine and was loaded on torsion and normal forces. Today I have restricted myself to show you only results for R-1 loading in order to save some time for discussion. And this is a test rig now. So here again there is a specimen. What is shown here in white, and you cannot see it really, is the area of interest. These four weld start and stop points, and these are four cameras mounted around that which took photographs of the weld ends at regular intervals of cycles. And well, again, this is a 3D scan of one of these weld ends which you can see here. And well, under axial loading, under pure torsion loading, under proportional and some non-proportional loading, we created failures, and nothing happens. Why not? I don't know. Okay, there should be some animations running by themselves. The first cracks you can see here in this weld end point here. You see it now. It's too late. Here is one of them. Here it comes out, and you see here the crack growing into the specimen, and finally there is some rupture. So we know exactly is the wrong word here in this environment here. We know where these cracks initiate. They initiate where they are expected to initiate. And well, I'm a civil engineer, and in my times it was forbidden to make such constructions, but the automobilists do so. I wouldn't have recommended that now. They wanted to know what is the life. And this is summarizing a figure of what we found out during our fatigue tests. On the left-hand side you have SN diagrams, so there is a stress amplitude, normal stress amplitude, and this normal stress is a nominal stress. It is simply calculated by dividing the applied force by the cross-section area of the weld, the nominal cross-section area of the weld. And on the right-hand side you see the diagram where the shear stress amplitudes are indicated over the life to failure, and also these shear stress amplitudes are nominal stresses, torsional moment, divided by the diameter of the weld. So we have a force pair, and then you divide that force by the cross-section area of the weld. So in the left-hand side, you can see here the results for pure normal forces in red, and on the right-hand side for pure torsional loading in blue. And what is indicated here with some other colors are combinations of torsion and normal forces. These are not as many experimental results as you might imagine here, because in the combination, one experimental result is here shown with two plots. So the combination here is shown on the left and on the right-hand side. However, only the normal forces can be plotted here, and the shear from the torsion can be plotted here. So in order to get some overview on what happened here, I have drawn here, or we have drawn a line here at the failure life of 10 to the power 5, and then we can read out from these experimental findings the nominal normal stress amplitude, which belongs to the testing of pure normal forces, and the shear stress amplitude to a torsion moment. And from these other lines we can read out the combination of normal and shear stresses, nominal ones, which have acted, and we can plot that in interaction diagrams. So I will restrict myself in the rest of the presentation to these interaction diagrams. We have actual force here. I could have plotted nominal normal stress also, so simply a vector, and here torsional moment amplitude belonging to that 10 to the power 5 life to failure. And what we see here is the result. Let us look at these results for stress relief specimens. So the specimen after welding for stress relief, and we had other test series where we tested these tubes in as welded condition. So we see now these interaction diagrams, and what might be interesting is that well, there's a sharp interaction between these both components, and the full symbols are for the combination of loads with no phase angle between the two loading situations or load cases. And we tested with those cases also with a 90 degrees phase shift between torsion and normal forces. And what we discover is that things become worse if we introduce this phase shift. So the interaction diagram comes closer to the origin here. And one of the known unknowns now is why in the as-welded conditions we have higher endurable moments and normal forces. Well, you will see whether somebody has an idea. Residual stresses may be an argument on that. So, okay, these are experimental results, and our task was to give these people in the design office of the University some method to arrive at a reliable estimate of these weld end positions. We worked on that for several years, and the demand was not to do fracture mechanics, because some of the German automobilists, the CEO has decided that they do not have cracks, and therefore we cannot perform fracture mechanics. Should I name the company? Daimler. And, well, they very much rely on fictitious notch rounding when they talk on fatigue lives of welded joints, and therefore we looked on the shape of such weld end geometries and tried to find out some equivalent geometry which is able to reproduce that notch effect which happens to occur in these weld ends. So this is what Esam Shams now did. So we introduced a weld with an end, you saw it, and now we round it here, so the toe and the root, notch root, and we decided after a lengthy study that at the toe we have a radius of 0.2 millimeters, and at the root it's 50 micrometers radius. It's very common, also in IIW recommendations. is now the typical weld end. We filled it with finite elements and calculated now notch stresses. Okay. Again, this weld end position. So I took away the inner tube. Please keep in mind, so the top of the figure, there is the inner tube. This is a piece of the outer tube when we make submodeling technique here, and here is the weld end position. So now the tubes are taken away. This is the weld with the rounding. And now I rotate it, and on the top half of the figure here, there is the inner tube, and here is the outer tube. And where these cracks initiate is quite clear. However, if you have such fictitious rounding, we would expect here some stresses to be high and give us some indication of crack initiation. So this red area is a bit magnified now here. So here are plotted the results of finite element calculation, linear elasticity. Plasticity is forbidden again. So you see now here for the normal force, the unit load case shows us that the maximum stresses are occurring here in this area of the sharp notch. And if we apply the torsion moment, the high stresses are appearing at this area of the fictitiously rounded sharp notch. Okay, we must accept that as it is. And then we took these unit load case results and tried to go ahead with now multi-axial strength hypothesis for calculating fatigue lives. So in non-proportional loading, you have this phase shift of 90 degrees between axial force and torsional moment. And what we did first is to calculate the easy things from Mises equivalent stress at one of these nodes, for example. And then if you calculate that for a cycle, you end up with some result. And the second half of the cycle, you get that. And this is now nonsense, because we know we have an R-1 loading. We must apply a sign von Mises version, whatever it makes sense or not, and find out some ranges of equivalent stresses, von Mises stresses. This must be done for several or many loads, because in non-proportional loading, you cannot say in advance where the critical location will occur. And then we searched through all the nodes and found out which one is the critical one, giving us the highest von Mises stress amplitudes. Then this von Mises theory ends up with some results, now expressed also in terms of this interaction diagrams. And what we find is for the in-phase loading, the proportional loading here in green, we get as expected interaction diagram looking like this, really acceptable. However, for the case of out-of-phase loading, phase shift 90 degrees, so these both unit loading case seem to completely decouple from each other. And I do not trust this line here. If Esan Shams would have chosen a ratio of amplitudes here, which points to that here, then we would have a sharp corner more or less. So there is a decoupling, and this is totally out of range. This is not what we found in experiments, if you remember my experimental results previously. So then we applied the principal stress or normal stress hypothesis. Why not? Try that. And what we found out is simply the same. There is not a real difference in the result. Well, we had promised to check also a critical plane approach, whether it works or not, and we took the simplest one, which we could find according to Findlay, and maximize that Findlay parameter. And we have chosen a K of 0.2, which to our opinion is close to Mises theory in a proportional case. This is how we figured out the range of shear stresses here in that plane under investigation. We find ellipses, and then took this one as the range. And if we now apply that, we end up with an interaction diagram which is looking the same as all others. And it is wrong, obviously, especially for the 90 degrees out of phase loading case. Okay, preliminary summary. Preliminary, there are more summaries today. So, the weld ends under nominal, normal, and shear loading. Fatigue cracks initiate at this transition zone between the weld toe and the weld root. The cracks initiate and grow out. And by the way, in order to do physically based predictions, we should make crack growth calculations. However, I mentioned it was not possible in this project. The idealized weld end model was created for assessing fatigue strength based on stresses according to linear theory. And although there is a very small and tiny region of the locations of maximum stresses due to the unit load cases, they decouple in the position where the local maxima occur. And not any of the multi-axial fatigue hypothesis is able to provide a realistic interaction diagram. So, one more, last one. The German automobilists also rely on what is found in the Fraunhofer Institute, so our neighbors in Darmstadt. Most of you know perhaps Professor Sonsino, he's the most prominent member of this Fraunhofer Institute, and at that institute they created several years ago a so-called stress-based curve hypothesis, and we were forced to apply that too. And what is that? It is a bit restricted in its application, so it can only be applied with if you have no mean stresses. You have sinus function for the plane stress situation, and nothing else is allowed. You have the allowance for phase shifts in the normal and the shear stress. So what they propose to do is to create from these known stress functions, these P and Q values. So this is the center of a Morse circle in the plane stress situation, and this is the radius of the Morse circle, and it is a time function itself, and the shear stress remains as it is. And if you insert all things, you can end up with a P function and a Q function and a tau function, and you plot that in this stress space, and the proportional case ends up to be some line here in that space. And if you have a phase shift introduced here, you will find that the surrounding box, so this rectangular box, is always the same, depending only on these amplitudes. And there appear ellipses with always the same surrounding boxes, and these ellipses are indication of the non-proportionality in the loading. And the hypothesis itself can be written in this way here. So this SSCH, stress-based curve hypothesis, is constructed in a way that you have this square root here, that is P and Q and tau amplitudes from here go in, and some magic factor in this parenthesis behind that. And there are now three constants built in here. This is first of all this alpha. Alpha can be chosen to be 1 or 0 or something in between. And if you choose alpha to be 0, then you end up here in this formula with a maximum stress. So then it's a principal stress hypothesis. If you insert 1, then you are back to Mises equivalent stresses in this square root. So if you do all this mathematical stuff. And then there are two further constants here. One is that lambda. This is the ratio of the semi-axis in this stress space. Here. Ratio of the semi-axis of these ellipses. So if you are proportionally on your way, then lambda is 0, and this cancels out, so a factor of 1. And the third and last factor is some material parameter rho, which you might choose to fit your results. So, and then we fit it. So on the left-hand side, rho is taken to be 0, and then what you see is again this decoupling, not so strong as previously shown. And now we can play around with this rho factor. Don't ask me on the physical meaning of that rho factor. This is a big constant from Fraunhofer. However, if we drive this screw such far that we introduce a rho value of 0.6, never seen before in life, or not even in the Fraunhofer Institute, then we can create realistic interaction diagrams. And now the German automobilists are content with that. So they can apply that. It is validated procedure. So there's a sense behind. I'm not sure. So preliminary summary 2, there might exist empirical hypotheses which can heal the geometric decoupling of local maxima by fitting functions and parameters. That's my conclusion so far. And the other one is the notch stress approach to fatigue assessment of welded joints. Applying this fictitious notch root rounding seems to have come to its limits when we're dealing with these weld-end situations. What should we do better? I mentioned crack growth or something like that, or identify here a sharp corner where all the unit load cases deliver their stresses at one and only point, and then maybe we find some interaction, but we haven't. If we do fracture mechanics for the slit between the tubes, we tried that some years ago. It is clear you have a stress intensity factor. However, if you arrive at this weld-end position, then you do not have the usual singularity at that point, and you run into other troubles. And last but not least, I'm not sure, and we had this discussion just now from Luca, I think, we skipped the plasticity, and whether we can solve these problems without considering plasticity, I'm really not sure. So the summary is this: much work remains to be done. I'm hoping for your ideas. I thank the money givers. So there is a report. It is publicly available. You can download this with many, many other results and tables. It's really available. And thank you for your attention. This is